Today we're looking at stationary points. So there's three different types of stationary points. We can have maximums, points of inflection, and minimums. So you can see all of those here. We can find stationary points by finding the derivative of a function, making that derivative equal 0, solving for x, and then subbing in those x values back to the original function to get those coordinates of the stationary points. We'll then look at a little while down the track, working out whether it's a maximum, point of inflection, or minimum, but for the moment we're just finding the location of those stationary points. The actual coordinates are very important. This chapter is kind of split into two, so I'm just going to do some stationary points work and then we'll do some rates of change work. Yeah, a bit confusing, but there we go. Find the stationary points of this equation here for t being greater than 0. So first step is to find the derivative, which in this case is 6t squared minus 10t minus 4. We make that equal 0, and I'm just going to factorize out the 2 here. So 2 bracket 3t squared minus 5t minus 2. Using the cross method, that will give us 3t and t, and then we're going to have 1 and negative 2. So just a quick little check for that one. So of course we're trying to see that they add up to our middle term, which they indeed do. So our brackets now are going to be, let's write it like this. So 3t plus 1. Just trying to save some space here, sorry team. And t minus 2. So we factorized now. And that would give us t being negative 1 over 3 and t being 2. Now we were told that t must be greater than 0, so I'm actually just going to ignore this altogether. But we want the stationary point, so I want to sub this 2 back into the original equation, and that's going to give me all of this. Oops, 13. So that is 16 minus, what's that for? So 20 minus 8 plus 13. So it's at negative 4, negative 12. So I believe that comes out to just be 1. So our coordinate of our stationary point is 2, 1. And again, using that domain meant that I could ignore my other t value that we were working out from there. The curve with equation y equals ax squared plus bx plus 12 has a stationary point at 1, 13. Find a and b. So really good question here. We're going to sub 1 and 13 in to this original equation first. So that gives us 13 equals a plus b plus 12. And I could write that as 1 equals a plus b. So that's our first equation. We of course need two equations to solve this, as we have our a and b values. And the other point that we've been told is that we have a stationary point when x equals 1. So let's find our derivative, which is going to be 2ax plus b. So that's our derivative. So our stationary point, so our derivative equals 0 when x equals 1, is that 0 equals 2a plus b. That's our second equation. So if I do 1 minus 2, I'm going to end up with 1 equals negative a, and that means that negative 1 equals a. Subbing that back into either of these equations, I'm just going to go into this one here. So we'd end up with 1 equals negative 1 plus b, meaning that b equals 2. So we now have our two solutions, a equals negative 1 and b equals 2. So this is a pretty challenging question. You might get these on a CAS, and you can see CAS paper, so you can see my CAS solution there. I defined the original function and then subbed in my various values, and it gives me my a, b, and c values, but we might want to do this by hand as well. So straight away, we're given this value here, and I can see that that is a y-intercept. And if I subbed in 0 for x and 5 for y, we basically end up with 5 equaling c. So that's a good start. We've made some progress already. Now I'm going to sub in my 2, 7 to my original equation. So that gives me 7 equals 8 plus 4a plus 2b plus 5. So that's going to give me, so 2, so negative 6 equals 4a plus 2b. So that is my first equation. Oh, technically my c equals was my first one, but anyway, derivative of this becomes 3x squared plus 2ax plus b, and we're told that we have a stationary point when x equals 2, so I'm just using that 2 value. So that's going to give us all of this. So it's at 412 plus 4a plus b. So negative 12 equals 4a plus b. So that is our equation 2. I'm going to do, let's do 1 minus 2. That's going to get rid of our a. So negative 6 minus negative 12 is positive 6. 4a minus 4a cancels, and 2b minus b is b. 2b minus, yep. So we've got our b value there as 6, and now we can keep working on this. So 4a plus 12, so that's going to be negative 18 equals 4a, and that, of course, is, well, yeah, it's going to be 9 over 2. That's as far as we can go with simplifying that one. And you can see that in our answers there. So we're feeling confident. The Kaz said we're correct, which is a great sign, and that's it. So this is the same kind of thing. I would suggest having a quick go on your Kaz with this one. So define the original function and go from there. Result coming in 3, 2, 1. So you can see here it's a pretty challenging problem to type in, but we can use our calculus in the menu items derivative at a point. Just be careful with brackets here. Remember, when defining this function that you need to write it as a times x cubed. Maybe it's easier to define the derivative as another function as well and then just sub in those values. But yeah, have a bit of a play with that, making sure you can do that on the Kaz. So like I said at the start of this video, the textbook kind of splits this into 2 chapters. It does a little bit of a recap of rates of change and application questions. So just make sure you're aware that the derivative is found by going through the process of differentiation. Remember that average rate of change is between 2 points, so that's different to the instantaneous rate of change. And we can obviously find the derivative by rule or by first principles as well. So there's a good example there. Let's do a couple of questions. So this first one's just a straight up Kaz question. We'd be defining the function, and then we're finding the average rate of change over the first 10 seconds. So that's when t is 0 and t is 10, as you can see here. Same for part 2 of part A, so that's 20 seconds and 0. And for how long is this model valid? So you can see here that we would only select this option here for our t value. So between, so I guess let's say when t is an element of 0 to 100 times the square root of 31 minus 5, and a curved bracket as well. Actually, we probably could have a square bracket there because the volume would be technically 0 exactly at that point. Oops, square bracket, there we go. So that's a bit of a strange question, but again, we're finding the t-intercept, or the x-intercept if you want to think of it like that, and obviously we ignore the negative value as we would not have negative time with our balloon leak. We may need to do some sketching with stationary points as well, so this is a pretty full-on question. There's a lot of substitution that we're going to be doing. As you can see, we have some endpoints with square brackets, so again, they'll be solid dots, which we've seen all this stuff before. So finding the coordinates of our stationary points, the first step is to find the derivative. So that would be 1 over 2. I'm actually just going to derive what I have in my bracket here. Because I don't have a squared or anything like that, it means that I don't need to use the chain rule. So this would become 3x squared plus 6x, and that's it. Because we're making this 0, it means that I can, at this point, multiply both sides by by 2, leaving me with 3x squared plus 6x. So I've skipped some steps there, but of course making the derivative equal 0 to find the stationary points. That factorized gives us this, meaning that x equals 0 and negative 2. So that's just the x values of our stationary points. I need to sub those back into the original equation, and when I do that, I come out with a half times negative 4, which is negative 2, and here, this one's a little bit trickier, so it's a half, so that's negative 8 plus 12 minus 4, and that comes out to be 0, I think. So there you go. So that's our coordinates of our stationary points. Find the average rate of change between these values. So I'm actually just going to write these really quickly as coordinates. So I need to find the average rate of change between these two coordinates. That's what this next section is asking me. And that would be -2 minus 0 over 0 minus -2. Oops, -2 over 2 becomes -1. So that's the average rate of change between those. Forgot to mention, I left the marking in here. This was actually a test question from a few years ago. So again, I just wanted to give you a sense of the kind of things that this would look like in an actual test. So we're almost there. We then need to find our endpoints. So by subbing in -3, we get the result of -2. I know I'm jumping fairly quickly there. And subbing in 2 would give us the result of 8. I'm able to do that fairly quickly by using the factorized form that the question's given us. So again, in a test, they're trying to help you a little bit so you can still sketch this graph, even if you had some trouble finding the stationary points or the average rate of change. We can keep working through from there. I'm just going to pause and do this quickly because it's going to take too long. That took me far too many goes to sketch and it still doesn't look great. But there you go. We have plotted all our points. We have solid dots for our endpoints as they were square brackets at the start. But again, having those turning points just gives us a bit more that we can work with. They ended up being our y-intercept and an x-intercept, so it didn't help a huge amount. But finding those stationary points was, quite beneficial and can be really helpful when sketching these graphs. The more points that you have, the easier it can be to sketch them. So this is one of the last questions from chapter 18b, in the Cambridge textbook that is. So I've obviously given you the solutions there. Just wanted to point out a couple of key things. Make sure you're adding units, particularly for our rate of increase, so part B, so kilometers squared per hour. Finding derivatives here, getting your notation right. So this is dA over dt, although that looks like a pretty weird D there. I'll try and fix that up. Oh, my pen's not working. Hold on. What a waste of time. Okay. Be really careful with the wording of part B here. So find the rate of increase of the area after 1 hour. That is when t equals 1. So if it said in the first hour, that would be an average rate of change. But you just have to be really careful and practice with the language in these questions, as it's easy to misinterpret some of these problems.